presentation will discuss the emerging pollutants in wastewater, their effects on human health, and the challenges of the removal from the natural environment. What are emerging contaminants? Emerging pollutants are chemicals and compounds that have recently been identified as dangers to the environment, and consequently to the health of human beings. Precisely, they have been labeled emerging because of the rising level of concern linked to them. In addition, many of these emerging pollutants have not been regulated under national or international legislation, hence posing a greater risk to their livelihood. Emerging pollutants, also known as contaminants of emerging concern, are the substances that are released in the environment for which no regulations are currently established. They are mainly organic compounds present as pharmaceuticals and personal care products, hormones, food additives, pesticides, plasticizers, wood preservatives, laundry detergents, disinfectants, surfactants, flame retardants, and other organic compounds in water generated mainly by human activities. A significant number of emerging pollutants resulting from point and diffuse pollution is present in the aquatic environment. These are chemicals that are not commonly monitored, but have the potential to enter the environment and cause adverse ecological and human health effects. Wastewater is contaminated by domestic, industrial, and commercial activity that needs to be treated before it could be discharged into some other water bodies to avoid even more groundwater contamination supplies. It consists of various contaminants like heavy metals, organic pollutants, inorganic pollutants, and emerging contaminants. Research has been doing on all types of contaminants more than a decade, but this emerging contaminants is the contaminants, which arises mostly from pharmaceuticals, personal care products, hormones, and fertilizer industries. The majority of emerging contaminants did not have standardized guidelines, but may have adverse effects on human and marine organisms, even at smaller concentrations. Typically, extremely low doses of emerging contaminants are found in the marine environment and cause a potential risk to the aquatic animals living there. When contaminants emerge in the marine world, they are potentially toxic and pose many risks to the health of both man and livestock. These pollutants include a variety of compounds such as antibiotics, drugs, steroids, endocrine disruptors, hormones, industrial additives, chemicals, and also microbeads and microplastics. There is an inextricable link between these pollutants and wastewater. Municipal, industrial, and domestic wastewater are, in fact, a primary pathway for their wide diffusion in the aquatic environment. While more research is needed, it is widely acknowledged that these emerging pollutants are increasingly becoming a hazard. With the increase in pollutants, the number of these synthetic chemicals is also enhanced. These emerging pollutants, or primary pollutants, or micropollutants, refer to those for which there are no standards and monitoring of present in discharged wastewater. The lack of scientific data on the fate and behavior of emerging pollutants in the wastewater also poses a risk to the ecological and human health. Certain emerging contaminants have been shown to interact with the endocrine system. There is scientific evidence to suggest that aquatic organisms have been affected. There is great scientific debate whether humans are affected at the environmental concentrations present today. What we know or don't know. USGS has detected many of these chemicals in water bodies throughout the United States. Many of these chemicals are routinely used by the average household. The widespread use of these chemicals allows for many points on entry to the environment. Emerging contaminants, such as personal care products, endocrine disrupting compounds, pharmaceuticals, and their transformation products, whose occurrence at trace levels in treated wastewater is of concern for human health and the aquatic ecosystem. According to United Nations Environment Program, wastewater treatment does not completely remove these chemicals from waste streams. Some of this even become resistant to the treatment process, or what we called as antimicrobial resistance. Why did this antimicrobial resistance are present in wastewater? Why they are not totally removed from wastewater effluent? But before we go further, let us discuss how this antimicrobial resistance developed.
Antibiotics. Behind the scenes, they enable much of modern medicine. We use them to cure infectious diseases, but also to safely facilitate everything from surgery to chemotherapy to organ transplants. Without antibiotics, even routine medical procedures can lead to life-threatening infections, and we're at risk of losing them. Antibiotics are chemicals that prevent the growth of bacteria. Unfortunately, some bacteria have become resistant to all currently available antibiotics. At the same time, we've stopped discovering new ones. Still, there's hope that we can get ahead of the problem. But first, how did we get into this situation? The first widely used antibiotic was penicillin, discovered in 1928 by Alexander Fleming. In his 1945 Nobel Prize acceptance speech, Fleming warned that bacterial resistance had the potential to ruin the miracle of antibiotics. He was right. In the 1940s and 50s, resistant bacteria already began to appear. From then until the 1980s, pharmaceutical companies countered the problem of resistance by discovering many new antibiotics. At first, this was a highly successful and highly profitable enterprise. Over time, a couple things changed. Newly discovered antibiotics were often only effective for a narrow spectrum of infections, whereas the first ones had been broadly applicable. This isn't a problem in itself, but it does mean that fewer doses of these drugs could be sold, making them less profitable. In the early days, antibiotics were heavily overprescribed, including for viral infections they had no effect on. Scrutiny around prescriptions increased, which is good, but also lowered sales. At the same time, companies began to develop more drugs that are taken over a patient's lifetime, like blood pressure and cholesterol medications, and later antidepressants and anti-anxiety medications. Because they are taken indefinitely, these drugs are more profitable. By the mid-1980s, no new chemical classes of antibiotics were discovered, but bacteria continued to acquire resistance and pass it along by sharing genetic information between individual bacteria and even across species. Now, bacteria that are resistant to many antibiotics are common, and increasingly, some strains are resistant to all our current drugs. So, what can we do about this? We need to control the use of existing antibiotics, create new ones, combat resistance to new and existing drugs, and find new ways to fight bacterial infections. The largest consumer of antibiotics is agriculture, which uses antibiotics not only to treat infections, but to promote the growth of food animals. Using large volumes of antibiotics increases the bacteria's exposure to the antibiotics, and therefore their opportunity to develop resistance. Many bacteria that are common in animals, like Salmonella, can also infect humans, and drug-resistant versions can pass to us through the food chain and spread through international trade and travel networks. In terms of finding new antibiotics, nature offers the most promising new compounds. Organisms like other microbes and fungi have evolved over millions of years to live in competitive environments, meaning they often contain antibiotic compounds to give them a survival advantage over certain bacteria. We can also package antibiotics with molecules that inhibit resistance. One way bacteria develop resistance is through proteins of their own that degrade the drug. By packaging the antibiotic with molecules that block the degraders, the antibiotic can do its job.
Antimicrobial resistance is a global health and development threat. It requires urgent multisectoral action in order to achieve the Sustainable Development Goals. Antimicrobial resistance is a global health and development threat. It requires urgent multisectoral action in order to achieve the Sustainable Development Goals. WHO has declared that AMR is one of the top 10 global public health threats facing humanity. WHO has declared that AMR is one of the top 10 global public health threats facing humanity. Misuse and overuse of antimicrobials are the main drivers in the development of drug-resistant pathogens. Lack of clean water and sanitation and inadequate infection prevention and control promotes the spread of microbes, some of which can be resistant to antimicrobial treatment. The cost of AMR to the economy is significant. In addition to death and disability, prolonged illness results in longer hospital stays, the need for more expensive medicines, and financial challenges for those impacted. Without effective antimicrobials, the success of modern medicine in treating infections, including during major surgery and cancer chemotherapy, would be at increased risk. Antimicrobials, including antibiotics, antivirals, antifungals, and antiparasitics, are medicines used to prevent and treat infections in humans, animals, and plants. What is antimicrobial resistance? Antimicrobial resistance, AMR, occurs when bacteria, viruses, fungi, and parasites change over time and no longer respond to medicines, making infections harder to treat and increasing the risk of disease spread, severe illness, and death. As a result of drug resistance, antibiotics and other antimicrobial medicines become ineffective and infections become increasingly difficult or impossible to treat. The emergence and spread of drug-resistant pathogens that have acquired new resistance mechanisms, leading to antimicrobial resistance, continue to threaten our ability to treat common infections. Antibiotics are becoming increasingly ineffective as drug resistance spreads globally, leading to more difficult to treat infections and death. New antibacterials are urgently needed, for example, to treat carbapenem-resistant gram-negative bacterial infections, as identified in the WHO priority pathogen list. Currently, resistant infections result in 700,000 deaths every year, but the global resistance-associated mortality is estimated to top 10 million lives per year in 2050. Transmission of AMR can spread between people, animals, and the environment via a number of different routes. The environment acts as a bridge for different compartments, between animals to compost to soil to water to sediments to sewage. Many studies have highlighted the impact of the diverse nature of the reservoirs of AMR genes, ARGs, on promoting the emergence and transmission of AMR organisms. Although it has been well established that the genetic transfer of ARGs is likely to occur between closely related species, recent studies have suggested that this transfer can also occur among phylogenetically distant species, and even among organisms belonging to distinct phyla, adding further challenges in the continuous evolution of new variants of AMR organisms. High concentrations of antibiotic residues, ARGs, and AMR organisms have been reported from environmental samples recovered from hospital and urban and treated wastewaters, and soils treated with animal manure. From the 1,466 articles that were identified, 63 studies conducted on wastewater samples between 2004 and 2018, published in the period 2009 to 2019, were included in the data analysis. The analyzed studies documenting the detection of ARBs and/or ARGs in different types of wastewaters are listed in Table 1. The source and type of wastewater samples investigated, and the key findings highlighted by these studies are summarized. Table 1. Detailed information on location and time of sample collection, structure of ARBs populations and/or ARGs detected. These studies highlight the role of aquatic ecosystems, particularly wastewater, as a key reservoir of AMR bacteria and ARGs in the environment. High levels of both ARBs and/or ARGs were detected in samples collected from different types of wastewater, including municipal sewage and influent and effluent samples from wastewater treatment plants. Conventional and advanced wastewater treatment plants have employed different biological, physical, and chemical processes to clean wastewater from pollutants and contaminants so that they can be reused and/or returned back to the environment. The efficiency of removal of AMR bacteria from effluent wastewater treated varies according to the treatment procedure employed. Another study demonstrated the detection of E. coli strains associated with neonatal meningitis, intestinal and extraintestinal serotypes in final effluents of wastewater treatment plants. High levels of resistance were identified in BFG bacteria isolated from wastewater treatment plants compared to those that have been recovered from human feces investigated. Chlorination is a widely used disinfection technology. The effects of chlorination on antibiotic resistome and bacterial community receive great scientific concerns, while the pathogens-associated health risks are largely unknown. With this concern, this present study used metagenomic analysis combined with the culture method to reveal chlorination effects on antibiotic resistance genes and their bacterial hosts through simulating the chlorination dosage with human health concerns in both drinking water and swimming pool. The resistome profiling showed that chlorination process could significantly decrease both the abundance and diversity of total anti-resistance genes, while with limited removal rates of 6.0 to 8.7% for opportunistic pathogens E. coli isolates. Hence, chlorination is not 100% effective in the removal of those bacteria in water effluent. This result poses a big concern for public health. Membrane filtration uses membranes to remove particles from water. The process is similar to conventional sand or media filters in that suspended solids are removed, but generally dissolved solids are not removed. Membrane filtration processes can operate under pressure or vacuum. These are the difference among filtration membranes. An ultrafiltration filter has a pore size around 0.01 micron. A microfiltration filter has a pore size around 0.1 micron. So when water undergoes microfiltration, many microorganisms are removed, but viruses remain in the water. Ultrafiltration would remove these larger particles, and may remove some viruses. And nanofiltration is a pressure-driven membrane process that lies between ultrafiltration and reverse osmosis in terms of its ability to reject molecular or ionic species. Nanofiltration membranes, organic membranes, or ceramic membranes can be either dense or porous. Reverse osmosis, RO, membranes play a key role in wastewater treatment units as they are used to remove salts and other pollutants effectively. One of the common disinfection processes is ozonation. It uses ozone O3. It is a strong oxidizing agent 2,000 times more powerful than Cl2, more expensive and more difficult to handle, and more commonly used for decolorizing and deodorizing.
Ozone is an unstable natural gas. A pleasant scent that fills the air after a thunderstorm belongs to the ozone produced by lightning. Its molecules are generated by a UV light or electrical discharge through pure oxygen or just dry air. When exposed, the oxygen molecule is split into two oxygen atoms. Then the atom connects to another oxygen molecule, and thus ozone is formed. The well-known smell doesn't last long because the gas is unstable and decomposes to pure oxygen soon without any trace. The half-life of the ozone molecule is just 20 minutes, but during the lifetime, it has an exceptional oxidation potential, which makes the gas an important element of modern industry. Ozone in nature is absolutely safe for humans, but its oxidizing properties make it the most efficient and the most environmentally friendly disinfectant. Being nature's own disinfection agent, ozone eliminates a large number of harmful contaminants like viruses, bacteria, or fungi. It is twice more oxidizing than chlorine, but unlike chlorine and other chemicals, unconsumed ozone reverts back to oxygen with no residuals. Also, ozone improves the effectiveness of biological and particulate filtration. The industrial scope of ozone is massive. Ozone has been used for drinking water disinfection since 1904. The other applications are water treatments and wastewater disinfection, odor, color, and taste control, cooling towers protection, aquaculture, food storage and processing, clean-in-place systems, laundry systems, medicine, surface sanitation, iron and manganese removal, soil and groundwater remediation, and many more. Industrial ozone is produced with special installations that are mounted on site due to the gas short lifetime. The only raw material for production is the oxygen and electricity.
Ultraviolet, UV light disinfection is getting a lot of attention during the coronavirus pandemic. The main benefit, its ability to kill pathogens like viruses and bacteria. UVC, also known as germicidal UV, includes wavelengths from 200 to 280 nm. This is the traditional form of germicidal UV that scientists have used to disinfect water, air, and surfaces for more than a century. UVC is effective at destroying and deactivating all kinds of pathogens like viruses, bacteria, mold, and fungus.
Natural and man-made water sources such as rivers, lakes, dams, streams, and stormwater tanks may contain living microorganisms, bacteria, fungi, or non-living structures like viruses, which can be harmful for human health. Therefore, water and wastewater treatment plants in developed countries test and treat water before it is used for drinking, bathing, filling swimming pools, food preparation, or cooking. At the same time, however, 60% of all infant mortality worldwide is linked to infectious and parasitic diseases, most of them related to inadequate water disinfection in underdeveloped countries. Chemical disinfection approaches like chlorine dosing damage the cell membrane of microorganisms and then enter the cell to disrupt the respiration and DNA activity. Chlorine also kills most viruses, but it requires retention times of up to 30 minutes or more. In comparison, UV light provides rapid, effective inactivation of microorganisms through a physical process. When bacteria, viruses, and protozoa are exposed to the germicidal wavelengths of UV light, they are rendered incapable of reproducing and infecting. Ultraviolet UV light is emitted by our sun. However, it's invisible for the human eye. On the electromagnetic spectrum, it's positioned between X-rays and visible light, with wavelengths between 100 and 400 nanometers. This spectrum is categorized as germicidal, meaning it damages DNA and sterilizes surfaces with which it comes into contact. For humans, suntan and sunburn are familiar effects of exposure of the skin to UV light, along with an increased risk of skin cancer. When microorganisms or viruses are exposed to UV light, their nucleic acids are damaged in a way that they are rendered incapable of reproducing and infecting. Bacteria absorb light for growth process, therefore high-energy UV light is absorbed as well and enters cellular RNA and DNA. This absorption of UV energy forms new bonds between adjacent nucleotides, creating double bonds or dimers. The longer the exposure to UV light, the more the thymine dimers are formed in the DNA, and the greater the risk of an incorrect repair or missed dimer. If cellular processes are disrupted because of an incorrect repair or remaining damage, the cell cannot reproduce or infect anymore. It has been proven that UV light treatment is a rapid and effective way to inactivate a wide list of pathogenic bacteria and viruses. Unlike chemical disinfection like chlorine dousing, UV light also eliminates protozoan parasites, which cause, for example, malaria. However, UV disinfection is usually a single-pass treatment, and if used insufficiently, bacteria strains could regrow during transportation from treatment facilities to private households. Thanks for watching.
In the Philippines, only 10% of wastewater is treated, while 58% of the groundwater is contaminated. Only 5% of the total population is connected to a sewer network. The vast majority uses flush toilets connected to septic tanks. Since sludge treatment and disposal facilities are rare, domestic wastewater is discharged without treatment.